All right, this maximum modulus, minimum modulus theorem, I'm just going to briefly explain. It's not going to be a proof, but you can turn this idea to a proof. And I like this idea better. Like I said, many of the theorem here is really just being familiar with what happens to the real differentiable function in the calculus of the real variable, and these things are a little bit strange. Also that once analytic and forever analytic, that's another thing in here. So what was the maximum minimum modulus theorem? If you have simply connected region like this, and then therefore it has simple closed curve around it, and if it is not constant function and analytic, then you cannot have a maximum, or especially the maximum in here. You must have a maximum on the boundary. That was the maximum modulus theorem, right? And our companion book, the Churchill and Brown, has a better proof to me than our Sham series textbook. So if you want a formal proof, it's really neat proof. You will understand easily how the proof goes using Cauchy's integral formula. But it is just like another magic of a Cauchy's integral formula and not really telling us what is happening. So I'd like to use a different idea to explain why this one, the complex function, cannot have the maximum modulus theorem here, maximum inside the region. So for example, one case, let's say if this point is A in here, and if f prime of A is not equal to 0, suppose that, and if it is a real valued function, you know it cannot have a maximum value in there, right? This is called local maximum minimum. If it is a maximum, it's because it's inside, and the particular is a local maximum minimum, therefore its derivative must be 0. And same for two variable function as well. But this is a very special two variable function. It's complex analytic. And remember what happened to the neighborhood around x equals a. And there's nice grid around it here, right? Remember this thing we did when I introduced the derivative of complex? And that goes to f of a in here, right? So what happened to these tangent vectors, these two tangent vectors? They're rotated and stretched, right? That's what happened to the tangent level. This is slightly more complicated version of a linear approximation. So this is how linear approximation, the linear approximation is always stretched and rotation. So this grid line really looks like this. A little bit stretched around and rotated around. There's no bending around and no curvy thing. It's a rotation and then stretch. So let's say that was a 0 over here, and that is f of a. That's the length of f of a. Is that right? And you can see over here, there's further away side, there's always some f of z whose length is slightly bigger than length of f of a. Don't you agree? That's what's going on. Right? If I choose that. And that, because it's local in a small neighborhood, is completely controlled by this rotation and dilation. There must be this value over here that is mapped to that. So there is a value very close to a. So under that function f, it arrives slightly further away from f of a. So modulus is always greater than f of a. So if it is a non-zero derivative in that point, you cannot have a maximum absolute value. There's always going to be a slightly bigger one. The next problem is that what if that we have that equal to 0, right? If that's the case, now you're going to use this analysis. And usually, if you look at the maximum modulus theorem, we assume this is not constant, right? Therefore, derivative is not 0 forever. Derivative 0 forever is going to be a constant function. So if the first derivative is non-zero and the function is non-constant, and it has a Taylor expansion always, right? That's the analytic theory. So it's f of z is going to be eventually going to be all the 0 times z minus a. It's a Taylor expansion. 0 times z minus a squared, go all the way up to some sort of a b that is non-zero, and z minus a to the n, and go on, and b is going to be non-zero. If it's all 0, it's going to be a constant function. All right. And there is some constant in there, f of a in there. Forgot to add in there. So this allows us to write this function f of z around the neighborhood of a. The derivative is 0, but it still gives us nice approximation. So let me use this curvy symbol in here. F of z is nicely approximated by f of a, that's this value, and plus b times z minus a to the nth power. Before, f prime of a non-zero, this n was 1. This time n is a slightly bigger. So if n is 1, it's going like this. When n is a slightly bigger than 1, if it is, for example, n is 3, then if you look at the neighborhood of a, you divide it into 3 pieces like this. And this piece, because you raise to the nth power, it wraps around, it gives you the complete picture. So if you only look at just not this entire neighborhood, 1/3 of the neighborhood, 1/nth of the neighborhood, then you will wrap around everything in here. All the neighborhood. This time it's a little curved, so that it's difficult to see, but it's wrapped around everywhere by looking at this approximation. So if this is f of a, there's always going to be some number out there further away because it's onto map just going from 1/nth of the piece, and there will be some point that is mapped to further away from the map. So this is kind of explanation of why it cannot have maximum modulus thing in there. Inside, it has to be the boundary. So if you look at, if it is a maximum on in here, if you look around outside, including the outside of the boundary, it gets larger and larger, right? So there's nowhere the local maximum minimum. That's pretty much more stronger statement, not the maximum. If you look at analytic function and entire complex plane, anywhere if you choose it, there's no local maximum. Around the neighborhood, there will be always a point that is slightly bigger than your given point. So if you close up like this, and then the maximum must be obtained at that boundary, but little outside the boundary, there will be a larger point. So interesting phenomena. It's really quite tied up to the Liouville's theorem that if it is bounded in the entire complex plane, it must be constant. Enter the Taylor series and Laurent series.